Hello, my name's Kathy Cook. I'm the project coordinator for the school's energy project. Welcome to our video where we learn about why we might have a drafty house. A very common reason for drafts is because a property has an open fire or a wood-burning stove and therefore a chimney or flue, which are actually holes in our roof. Having a permanent hole in the roof will consequently draw cold air in around badly fitting doors and windows in the house, whether the fire is alight or not, making the house chilly and drafty. This is called the chimney effect or stack effect. You can find out more about this on the Energy Saving Trust website and about what you could do to try and combat it. However, there are also other reasons for us having a drafty home in the winter, and the school's energy project has used its high-resolution thermal imaging camera to try and find out more. For example, when we have warm air circulating around a room which then comes into contact with cold walls and cold windows, we may then be getting unpleasant drafts due to convection currents. The thermal imaging camera has captured some interesting footage of convection currents in hot water as it cools down, and these may help us understand what's going on. But before we go any further, let's briefly explain what convection currents are. Well, when part of a fluid becomes warmer, its density will get less, and it will consequently get lighter, so it will rise. However, that part of the fluid may then lose its warmth and become cooler, so its density increases and it gets heavier and as a result starts to sink. In closed systems, a continuous cycle may then become established, with cells or packets of fluid rising as they warm and then falling again as they cool. Convection currents occur in many everyday situations, for example, in a saucepan of hot water on the cooker, or most notably with the weather, for example, when air rises as the sun warms it up. In this experiment, we have only been able to look at the natural convection currents set up as hot water cools down naturally. We've not been able to look at forced convection, which is what happens when we force heat into a fluid and circulate it. Now, if we're going to look at hot water with the thermal imaging camera and try to imagine its warm air, we should perhaps start by asking ourselves, is water similar to air? And will observing convection currents in hot water be helpful for understanding how warm air circulates in our homes? Well, we know that water is a liquid, and unlike solids which can't move, a liquid can move. A liquid can flow freely. It also has no fixed shape, so it's therefore classed as a fluid. I think we can definitely say that water is a fluid. Then let's think about the air that's all around us. This is a gas, not a liquid. But gases can also flow freely. They also have no fixed shape. So gases are classed as fluids as well as liquids. So the air around us is definitely also a fluid because it has no fixed shape, as we can see from this image of air bubbles and these mouldable balloons full of air in all sorts of different shapes. And these hot air balloons full of air. So if air has no fixed shape, it must definitely be a fluid. So we can see that both liquids and gases are fluids, and thus both water and air are fluids. Water may be a lot more dense than air, but because water and air are both fluids, they will actually tend to behave in a similar way when exposed to similar conditions. The other helpful thing about water is that we can observe its behaviour using the thermal imaging camera, whereas we can't see air movements. Observing air currents is a lot more tricky and requires specialised scientific techniques, such as using smoke trails, as in a wind tunnel, or Schlieren optics, but even these have their own practical limitations. Consequently, observing air currents in a house isn't easy. So, instead of trying to observe air movements directly, it's a lot easier to observe water movements with the thermal imaging camera. And what we see with the camera can give us a good indication of how air might behave in similar circumstances. So we set this experiment up with our high-resolution thermal imaging camera in video mode to have a look. We initially created a very simple setup so we could observe how hot water behaves in a container when that container is placed in a cold environment. Here's what we used for this first part of our experiment. A large round cake container made of polypropylene, 26 centimetres, that's about 10 inches in diameter, and a kettle to boil the water to go in the container. We needed about 8 litres. And then we sat the container of hot water on the bottom of a bath with cold water all around it. Importantly, we left the water in the container to settle for several minutes so that the turbulence created by pouring the water in from the kettle had completely subsided. Note also there's no lid on the container. That's because the thermal imaging camera needs to have direct sight of the surface of the water to capture the images. So part of the cooling experienced by the hot water will have been because it was cooled to some extent by the air above. So, in a way, this arrangement of a container of hot water with no lid sitting in a bath of cold water is somewhat similar to a house in winter. A house that in this case has no insulation in its roof or its walls and is being cooled rapidly by a cold wintry environment outside. Thankfully, there aren't many houses like that with no insulation these days, but it's still useful to look at this extreme case to see what might happen to warm air in an uninsulated space like this. So, what did the camera see? The red shimmering you can see is warm water vapour coming off the hot water. Ignore that and look at how the water underneath the steam is moving in cells. Then look at how the very whitest cells are located around the periphery. So that means the hottest water is at the edge of the container. But the container is surrounded by a lot of cold water in the bath. You can see the purple area all around. So its side walls must be the coldest part. So why is the hot water there? What is going on? If you've already watched our part 2 video on how to do a thermal imaging survey of your home, you'll remember that we said that heat always travels from hot to cold, and we also said that the bigger the temperature difference, the bigger the driving force, and consequently the faster this movement will occur. A useful way to think about this is to imagine that the cold is effectively a magnet, attracting the heat towards it. And the wider the difference in temperature between the hot and the cold, the stronger the pull of this imaginary magnet. So does this then explain what's going on with the hot water in the round container? Let's go back to the video and watch carefully. As we've already noted, the hottest water is very visible as the whitest cells right against the cold walls of the container. These cells of hot water are evidently rising up the walls and arriving at the surface where the camera can see them. Remember, the cold walls are hardly going to change in temperature at all and will remain cold throughout this experiment because they're being endlessly cooled by the much larger volume of cold water in the bath. So these white cells of hot water are evidently getting cooled fairly quickly as they rise up the walls. The strong cooling of the container's walls will be continually drawing yet more hot water towards the cold walls, where that too rises upwards. This continual uprising of more hot water against the cold walls then displaces the previous cells of hot water which were already at the surface, and then pushes them away from the cold walls and back out across the surface of the water towards the middle. But of course, these cells of warm water at the surface that are being pushed away are now a lot cooler. And we can see this cooling happening in the video. The cells leaving the periphery are turning pinker and then redder in colour as they cool. Now notice the spirals and vortices as the redder, cooling cells of water get darker and darker, and then they descend quite quickly down below the surface into the depths. In fact, the temperature of the descending cells of water are about 2 to 3 degrees centigrade cooler than the cells at the periphery of the container. That means their density will be increased and they will be getting heavier as a result, so it's not surprising that they sink. Now let's imagine that our container of hot water is instead a house full of warm air in winter, with endless amounts of cold air outside, but with no insulation at all. Those downward spirals we've just seen in the video clips would instead be very strong downdrafts of cold air. That would not be pleasant. So this initial part of our experiment has helped illustrate several things. It shows how in a house, warm air will naturally move towards the coldest surfaces, for example, cold walls and windows, and will then rise up these cold surfaces, but at the same time get rapidly chilled. Then once this air reaches the ceiling, it's pushed out of the way by further warm air rising up from beneath. And because there's nowhere else for it to go, the air at the ceiling has to move out across the ceiling, but then, because it's been cooled, it's heavier and then begins to sink into the room. This downward flow of air also helps to propel the warm air travelling across towards the cold walls. And in this way, a cycle is set up. Unfortunately, the bigger the temperature difference between the warm air and the cold surfaces in a room, the more this speeds up the cycle of air movement, causing the downdrafts from the ceiling to be more vigorous and chilling. Having seen what happens with the uninsulated container, we then carried out the second part of our experiment. We used the same round cake container, but this time we wrapped it up to simulate how warm air in an insulated house might behave. Again, remember, our observations were of the natural cooling of the container contents. No heat was being injected. We added our insulation to the container in two parts. Firstly, we sat the container on a set of raffia table mats to keep the base of the container warm. And then secondly, we folded a towel lengthways and wrapped it around the outside of the container. We finally placed the whole assembly in a black plastic dustbin bag, pegged in place with closed pegs to protect our insulation from getting wet while it was sitting in the bath of cold water. So in this video, we can see how the hot water behaves in our insulated container. First of all, this time there clearly isn't a white ring of small cells of hot water positioned all around the periphery of the container. This tells us that the outside walls of the container are no longer cold, which is good. That's because they're wrapped in insulation. We can also see that the cells are much larger, which indicates that there's a generally more uniform temperature across the surface of the water. And lastly, we can see that the movement of the hot water cells is much slower, which means that the cooling of the hot water is less rapid. So it appears that keeping the sides of the container warmer by wrapping them up results in much less cooling and therefore less convection currents. And that's a good result. And that makes sense, doesn't it? As we know that it's the temperature difference that drives the speed of the cooling. So with the insulation in place around the container, the temperature difference between the inside and outside of the container walls is a lot less. So less convection currents in the water is exactly what we'd hoped to see. The main part of any cooling going on this time is probably a small amount from the surface of the water, because we can't have a lid on while we're thermal imaging. So in summary, this part of our experiment simulates what happens in a well-insulated house. There is very little heat loss. And as there are no cold surfaces, the warm air inside is not moving to the walls, and therefore no convection currents and draughts are being created. That will feel a lot more comfortable. Then we carried out the third, final stage of our experiment. This was to create a window in the insulation around our container and then observe the natural cooling process and how this affected the convection currents. We did this by simply wrapping the towel around only 2/3 of the outside of the container, leaving 1/3 of the container uninsulated. You can see the window we created is at the bottom of the screen between the two clothes pegs that hold the black bin bag in place. Watching this snippet, you can see the white cells of hot water appear to be moving towards the cool surface of the window from several directions. Then, in this next clip that we filmed a short while later, the warm cells are rapidly sinking down below the surface of the water just a short distance away from the window. Watch the spiralling vortices in the darker red area. So it appears that without a uniform layer of insulation around the entire container, the patterns of movement set up within the hot water are somewhat uneven and unstable. Applying these observations to our homes during the winter, even though we may have an insulated house, in those rooms where we have full-length glazing, these large, cool areas of glass will be certainly perceptibly cooler than our insulated walls, regardless of whether they are double or triple glazed or perfectly sealed and leak-free. We can resolve this problem. After sunset, every day, when there's no further thermal gain to be had from the sun, we can simply close the curtains. That's a very straightforward solution that will stop the draughts and really help to cut down our heating bills. And if there aren't curtains, the best thing to do is to find some good heavy material, get it made into full-length curtains with either thermal lining or blackout lining. The curtains need to go right to the floor. If they're about 2 millimeters just too long, that will be perfect, as the bottom of the curtains will then just sit nicely on the floor and block any draughts from coming underneath from the cool windows. Obviously, these thermal imaging videos are only brief observations of some fairly rudimentary experiments we have set up in a bath of cold water, but they have usefully demonstrated the key principles of what happens to the warm air in a house when the outside of that house is being continually cooled, as it will be in the winter. So, what have we seen? Firstly, we've seen that heat always travels from hotter to colder places. In our homes, the cold places will be open doors and windows, cold glass, uninsulated ceilings or walls, and any holes or gaps in the structure, such as uncovered keyholes or extractor fans without shutters. Then we've seen that the bigger the temperature difference, the quicker the heat will travel to the cold places in our home, and consequently the more vigorous the air currents and draughts we are likely to experience. And we've learned that the colder the cold places are in our home, the more the cold areas will act like an imaginary magnet, drawing any warm air towards it, as we saw in the video of the uninsulated container. So, what have we been able to conclude? Well, we've been able to conclude a couple of really important points. Firstly, we've shown that insulating a home is vital for helping to prevent heat loss and is also essential for improving comfort. And then critically, we've observed how large gaps like patio doors in the insulation layer are likely to cause very noticeable heat losses. We've seen how this can cause uneven air movements, particularly near the windows, compromising the comfort in these rooms. And we've learned that the simplest solution is to hang heavy curtains across all full-length glazing and to ensure that we close all curtains at sunset so they act as a form of temporary insulation that we put in place every evening. We hope you've enjoyed this video and found it interesting. If you are interested in having a thermal imaging survey done on your home or in doing a survey yourself with one of our loan cameras, you can go to our website www.schoolsenergyproject.org.uk to find out more. Thank you for watching.